Welcome to Math 150, Section 2, Lecture 9-ish. What we're going to do today is the most, I think, technical part of the semester. We're going to do stuff related to the chain rule, which will help us with maximization and optimization. So one of the advantages of flipping the class like we're doing is it actually frees up time to really go into the difficult parts of the course and not be as pressed because you are doing a lot of the good work at home. So if there's ever things that you're reading that you're having trouble with, by all means, please let me know. But by freeing up some time, it means we can actually spend a little bit more time on this. And in particular, we can actually talk about some of this material before you get to it in the book and the lecture later. So you'll see the chain rule again, you'll see linear approximations again, you'll see Lagrange multipliers again. What I want to do today is just motivate where all of this stuff is coming from. All right. I did risk asking this in section 1. How many of you have seen a proof of the chain rule in Calc 102? So basically, it was taught biblically like Moses coming down from Mount Sinai with some commandments, and this is how thou shalt use thy chain. Okay.
I think I do, but I'm not.
Although, given what my daughter just saw for Pi Day, where we celebrated on March 14th because pi equals 3.14, sometimes it's better not to see. All right, so the chain rule, so let's say I have a function a of x is f of g of x. So whenever you hear the word of, you should be thinking chain rule, at least in a math. And the rule is a prime of x is f prime of g of x times g prime of x. The most common mistake is people forget to evaluate f prime at g of x. And that's a mistake that you should not be making because there is no other place you can evaluate f for f prime, because we start off by evaluating f at g of x. So when we calculate its derivative, that should be at g of x too. Another way to think about what's going on is you start off here with some point x, and then you have this math g, which takes you to this point g of x, and then we apply f, and that takes us to f of g of x. So when we calculate f prime, we actually calculate at this point, which is the point g of x, and that's where we are putting f, that's where we're putting f prime. As an example, imagine we have f of x is the square root of x, and g of x is x plus 5. If I look at a of x, that's f of g of x, there's two ways to do this. The first way is, look, f of input is square root of input, g of input is x plus 5, is input plus 5. It doesn't matter what letter I use when I define. I'm just giving you a rule. Some people might say maybe f of y equals square root of y, just use a different letter from what they're using for g, but it's okay. We can use anything we want. So one thing is say, well, g of x is x plus 5. This is just f of x plus 5. So it's just the square root of x plus 5. The other way to do it is to say, well, f of g of x, f of input is square root of input. What's the input? So in f of g of x, what's the input of f? It's just g of x. So another way is to say that this is just going to be the square root of g of x, which will then also get us back to square root of x plus 5. What would we get if we calculate a of negative 1? So what would a of negative 1 be? 2. What about f of negative 1? Yeah, we don't really want to do this. We're supposed to be having real value functions. The problem is f is not defined at negative 1. It is, however, defined at g of negative 1, which is 4. So hopefully this example reminds you why we have to be careful about how where we evaluate these functions. All right, what I want to do is a proof sketch. So if you've ever seen a sketch artist at a birthday party or at a park, their goal is not to have a complete, perfect capture of the image. It's to capture the key features so that when you look at it, you can get a sense of what's going on. You can identify who's being shown. I'm going to give you a proof sketch of the chain rule. It is not completely rigorous. I am resisting my temptation as a theoretical mathematician to give you the completely theoretical, rigorous proof. If you want to see that, happy to talk to you. Happy to give you stuff to read. I'm going to give you an almost proof. And I will tell you exactly where it goes wrong. If you want, please be watching carefully to see when we do something illegal. Very subtle, but we will do something almost surely just a little bit illegal. So what is the first step in every proof of every differentiation law? They all start the same way. What do they start? Good, they start with the definition. A prime of x is the limit as h goes to 0 of a of x plus h minus a of x over h. If you're proving product, quotient, chain, sum, all of them start this way. Step 2 is that you just substitute what a is. A is just f of g of x. This is just the limit as h tends to 0 of f of g of x plus h minus f of g of x over h. All right, so this is the start of the chain. This is the start of the proof. So far, we're just following our noses, doing everything standard. What I'm going to do now is something completely illegal, just to see what happens if the word is truly, truly illegal. Instead of having g of x plus h, what if that was just g of x plus h instead? It's not. I know it's not, but let's just see what would have happened. If that was g of x plus h, then we would have f of g of x plus h minus f of g of x over h. Ooh. So does that look like anything you've seen before? What does this look like? The definition of what? Of which function? Be specific. It looks like the definition of the function of which function? Which function does this look like the derivative of?
A of x.
Not a of x. F of x. At what point am I differentiating f of x? G of x. This looks like over here. This would just be f times g of x. So if g of x plus h was just g of x plus h, then this whole thing would just be f times g of x. It's not. But it shows you maybe, okay, here's a little bit where the g of x plus h is coming from. G of x plus h is probably pretty close to g of x plus h. It's different by a little bit. If instead of having an h, if I had a 2 over here, I would want to multiply a 2 over here, so that's the same change over here, and then multiply by a 2 to cancel that, and I would get 2 times f prime of g of x. If this was a 3, I'd multiply by 10 and get 3 times. Oh, maybe g of x plus h looks like g of x plus maybe g prime times h. And so if we do g of x plus h is g of x plus g prime of x is plus small error, that's going to kind of give us the f times g of x times g prime. So that's one way to see it. Another way is to multiply by 1. I want to multiply by 1 in a really good way. We've got g of x plus h minus g of x. What could we multiply by 1? How can we multiply by 1? So they're give us some squares, not going to really help. Another way to try to figure out what we want to is we want to get a G prime of that. What could we multiply that might go nicely with the G prime? On Wednesday, I will bring in the impossible Rubik's Cube to show you how a perspective of looking at things the right way. Depending on how you hold up the cube to the light, the squares have different colors. So the color is not constant as you turn it around, which is one. How do you look at this the right way? That's the hardest question I get. I want to get a G prime. What can I multiply by to try to give me a G prime? What does G prime look like? How would you define G prime? G prime is that. What do you need for G? Okay, so if you take out yeah, what do you get?
You get the definition of G prime.
So what should I multiply by? I need to put something in here to combine with this and give me G prime. What's the definition of G prime? Someone say G of x plus h minus G of x over h. What should I multiply by to give me this? So what is it? G of x plus h minus G of x over G of x plus h minus G of x. So if I do that, I can now group the h with that. Now I'll have the limit as h goes to 0 of f of g of x plus h minus f of g of x divided by g of x plus h minus g of x times g of x plus h minus g of x over h. What's the limit of a product? Product of the limit. What does this piece over here go to? G prime of x. That's looking really good. Now, what about this over here? F prime of g x. So we're going to see so many different definitions of the derivative today. Remember, one of the definitions was f prime at a is the limit as x goes to a of f of x minus f of a over x minus a. And if you look at that, that looks the same. You know, a is really g of x, and x is really g of x plus a. Now, in this limit, we take any path of x going to a. This is going to be a special path, but that's fine. If the limit exists no matter what path it takes, the limit exists if we go along our special path. So what would this limit be? What would the first factor converge to? What would the first factor converge to? Using this as our definition of the derivative, it's just going to be f prime where? At g of x. And there's the one variable chain rule. Now we did something illegal, potentially. So going back to our biblical imagery, what is the thing that thou shalt not do in a math? Thou shalt not divide by 0. Where could we have divided by 0? What did we do? We might have accidentally divided by 0. I'm sorry? Well, G prime over here is not dividing by G prime. Where did we do anything? There's only one place we really use something new. When I multiply it, what if g of x plus h equals g of x?
But h can't be 0.
H can't be 0. And so you never want to tempt the mathematician to be evil and cruel and create pathologically bad functions because we can. And in fact, I'm having a discussion with one of my colleagues about the second derivative test where what if the second derivative is not continuous and you still have the second derivative test? What if I give you this strange function, g of x is x to the 4 times 1 over x, if x is not 0, and 0 if x is 0. It turns out this function is differentiable, it's continuous. Sign is going to really oscillate when x is small. And in fact, this function is going to have infinitely many zeros in an arbitrarily small neighborhood of the origin. And so if I look at g of h minus g of 0 with this function, I will have infinitely many places where they agree.
Well, wait.
And so we can be evil. Now, you can put a little asterisk and say, okay, I will only use the chain rule when I'm in a situation when g does not have some pathologically bad property. That in a small neighborhood about x, g of x plus 8 is not equal to g of x. If g prime of x is positive, then you're okay because you have a speed. And if you have a speed, you're not going to be equal in a small neighborhood. So as long as g prime of x is positive, this is fine. I don't want to go into all the technical details, but I always want you to know when I am trying to sweep something under the rug. When I am saying, see, look how nice the proof is. Well, this is where the technical issue is. I really like this proof because I think it is illuminating in terms of what's going on, but you have to be careful about one of the issues. This is the one variable chain rule. And there's lots of applications of the one variable chain rule. What we want to do now is we want to try to extend this to several variables. So we're going to have some function, a of something, is going to be f of g of something. I'm going to set up a little dictionary to say where things go. G, f, and g. Right, and I want to see how this goes to the bottom. The easiest thing is going to be if g has how many inputs. What's the easiest number of variables to try to understand? 1. So let's say g has 1 input, so it goes to r. And let's say it goes to a point in 3-dimensional space. You draw x, y, z. It goes to r. So g is a map from r to r3. Yeah, no idea. Okay. F, how many inputs does f have to take? If g takes 1 input and gives me 3 outputs, how many inputs does f need? 3. It has to have the same number of inputs as g has outputs. And let's make f a real valued function, so it will send a triple to a real number. Think of it as a point on the Earth's surface, and it's going to give me the temperature. And then the last thing is a. How many inputs does a take? 1. It's f of g of t. It has 1 input. And how many outputs? 1. So if I look at what's going on, this is not the most general case of the chain rule. In one sense, it's very easy to fix. In one sense, it's a little bit harder. The easy sense is, well, what if f had multiple outputs? I had maybe f1, f2, f3, f4, f5. Well, that's not a big deal. I just apply things multiple times. And I can just apply things to each component. So having more components is not a big deal. What's a little bit more of a deal is if g has more inputs. It's a little bit nicer if g only has one input, but with a little bit more work, we can handle it. We are going to see the chain rule again. This is the pre-chain lecture. We're going to do a lot with it, but you will be seeing it again. Sometimes instead of g of t, I might write c of t for g of t. Where c of t is something x of t, y of t, z of t. So I have some interval here. I have some point c. And I have some curve c, and this will be the point c. Okay. So you give me some points in time, and I give you a place in space. We've seen something like this, the equation of a line. We did c of t dx, and so on and so on and so on. We can calculate the derivatives here. X would just be instead of x, y minus c would just be y, and so on. Or if you want to put it all together, c minus c, x of c, y of c, x minus c, y minus c, z minus c, would just be our vector v. Which makes sense because, in a line like this, we're moving at a constant speed in a constant direction. So this is the simplest example of a curve that we've seen. Okay. So what we want to do now is we want to try to figure out what would be the derivative of this function a of t, which is f of t of t or f of c of t. And then we'll see application rules. So there's a lot of ways to study. We're going to look at a of t is f of c of t. And I could go with the definition of the derivative. I could have f of c of t plus h minus f of c of t over h. And if I do that, I would have some point x of t, y of t, z of t, and I would end at x of t plus h, y of t plus h, z of t plus h. I'm not going to do it. If you want, I have notes, and I can play the game of making small changes. The first is I could add 0 and get to the point x of t plus h, y of t, z of t, where I just changed the x code. And then what would I change next? Y. And then I would go from here to x of t plus h, y of t plus h, z of t. And I would look at f of this point minus f of this point. Okay, well, that's f of this point minus f of this point plus f of this point minus f of this point plus f of this point minus f of that. And all the stuff in the middle would cancel, and I would group things, and I could do things like that. That is one way to try to do it. This is basically adding zeros, lots of adding zeros. If you want, email me, and I will make sure that you have a handout to look at where it will go through the calculation ways. I'm not going to do that calculation. You could do it like this. What I want to do is I want to do another one. And I want to look at what's going on. So remember, another definition of the derivative is the tangent plane does a good job. The tangent hyperplane does a good job. So in today's lecture, we're using all three definitions of the derivative. The standard one with h goes to 0, then we use x going to a, and now we're using the tangent plane definition. So a differentiable means the tangent plane is great. Let's think about what's going on. I have f of t of t plus h. Right? And I want to use my multi-variable calculus knowledge to try to approximate that based on where I started. So what will be my initial approximation? The easiest guess for f of t of t plus h. If I tell you nothing else, and I told you at time t, we're 17 miles from home, where are we at time t plus h? 17 miles from home. We know nothing else, right? We don't know which way we're going. We don't know how fast we're going. So the first thing is that approximately f of t of t, right? But then the tangent plane says, well, then take the gradient of f at C of t and dot it with how much you've moved, the distance. C of t plus h minus C of t. These are vectors. That's where I started, that's where I moved. This is how much I've moved, its magnitude and direction. As I take the gradient at C of t and dot it with the movement. And that should be a pretty good approximation for my function. So let's unwind this a little. I really don't care about this term because this term is constant. Let's expand this out. It's dx at C of t, dx y at C of t, dx dz at C of t. It's annoying to keep writing the C of t's because it's taking up a lot of space. And so I am going to take advantage of the fact that I am on a blackboard, and I can erase all this over here, and I can use the fact that I have the entire blackboard to write. And so I will write this over here as dx at C of t, dx y at C of t, dx dz at C of t. And now I have to dot it with C of t plus h minus C of t. And remember, C of t is x of t, y of t, z of t. It's where I am. So this is going to be x of t plus h minus x of t, y of t plus h minus y of t, z of t plus h minus z of t. So when you see x of t plus h minus x of t, if you are very quiet, you can hear it yelling at you to do something. What algebraic thing would you like to do? What does x of t plus h minus x of t look like? Yeah, you want to divide by h. Are you allowed to just divide by h because you want to? No. So what can you do that allows you to divide by h?
Do the other side.
So you can divide the other side by h, or
Multiply.
So I divide by h, divide by h, divide by h, and then multiply by h. What I get is where I am is approximately where I started, plus how my function is changing at that moment in time, times my velocity vector at that time, times the amount of time that elapsed. So this is looking like the gradient of f at C of t dotted with c prime of t and h. So to approximate how much I've changed, it's the gradient at my point dotted with how much I'm changing, the speed at that point, times the elapsed time. What direction should c prime of t be to maximize this change? How can I make this dot product as large as possible? So which direction should I choose for c prime of t to make this dot product as large? Parallel with the gradient of f, right? Because if they're parallel, then the cosine of theta is 1. So if c prime of t is in the direction of the gradient, that's my fastest change. If I go in that direction, I change the fastest. If I go in the opposite direction, instead of increasing at the fastest rate, if I go in the direction of speed, I decrease if I go in the direction of not the gradient of f, but negative gradient. What if c prime of t is perpendicular to the gradient? Dot product is 0. So what's happening to how much change is happening? There's no change. So we're beginning to see a little bit of the geometry coming into play. And what I like about this is we're really seeing that the different problems, different definitions, different perspectives of that. All right. So let's take one of the simplest three-dimensional surfaces. What's the simplest three-dimensional surface? Cube, circle, sphere. What did you do? Sphere or cube?
I feel like you are pretty.
So for the cube, I need to say x squared plus y squared plus b squared equals r squared. How would I write down the cube? The cube is a nice shape, but it's not as nice to write down as the sphere. So let's imagine g of x, y, z is the function x squared plus y squared plus b squared. I want to look at points where it equals s. So this is going to be a sphere of radius s. Nope. It's going to be what? A sphere of radius square root of s. I can write this as square root of s. So as long as s is greater or equal to 0, no problem. Oh, we have a term for something like this. Do you remember the term? For the set of inputs that are evaluated by your function to the same value. Wonderful. It's the level set. Now, normally we talk about the level set and we use C. Why am I not using C? Because C is for
You.
no.
Oh.
There's a mathematically correct answer and there's a substantively correct answer. But the physics answer. What are we using C for in this class right now today? The function of time are curve. So I want to keep C for curve. So I don't want to use C over here because then I would have little c by itself as the value of the level set, and little c with parentheses is the curve evaluated at time 2. So we're going to use C of t is x of t, y of t, z of t. This is our curve in space. And that's why we're going to use the letter S for surface or S for step, because I want to keep C preserved for curve. Okay? And so imagine we have this function, A of t is g of C of t. And imagine no matter what value t you take, g of C of t is always good. So you're staying on the surface. You're staying on the level. So if you want, if I have a sphere like this, I have some path like this, my C, and I'm staying on my sphere. We have two ways to differentiate. You can take the derivative directly, or you can use the chain rule. Since the class is split due to COVID into half, I will do one half, I will do one, and you do the other. Would you like to use the multivariable chain rule, or would you like to differentiate the function A of t equals s for all values of t? Which one do you want to do? Okay, so for all values of t, A of t is equal to s. What is the derivative? Every moment in time, the value of your function is s. 0. Right? What's your speed? Because every moment in time, your s units from home. Think of it as, this is my distance from home. My speed has to be 0. So we know a prime of t has to be 0. And that's the easy way to take the derivative. But we just talked about the multivariable chain rule. Foreshadowing the out of the great lecture. Let's use that. So let's take the derivative. Well, what is the derivative to use the chain rule? It's going to be the gradient of g. Where do we evaluate the gradient of g? CFT, always at CFT. If we evaluate G at CFT, we evaluate its derivatives at CFT. So that's the biggest mistake people make in the chain rule is they don't evaluate things at the right point. If a function is evaluated at one point, its derivatives have to be evaluated at that point as well. So it's degraded G at CFT, dotted with C prime of T. And what this is telling us is no matter what curve we take, so long as that curve stays on the surface, the instantaneous direction of motion is going to be perpendicular to the gradient of G. If I'm staying on the sphere, yeah, the instantaneous moment of strength, that's going to be my C prime of T. Question?
So like when you write a prime equals 0, would you actually say like it's with respect to S?
Well, here, well, no, well, S is not a variable. S is our constant value.
So it's taking the derivative constant.
It would be 0.
Yeah. So like if you were to take it with respect to like G of T, wouldn't you get what's going on?
Well, that's why these two are equal. I've calculated A prime two different ways. One way is, look, A prime is A of T equals S. So A of T is always S. The derivative with respect to T is 0. The other way is I'm taking the derivative of this with respect to T. And that involves looking at G of C of T plus H minus G of C of T divided by H to the limit. And we saw that basically is equal to this. You remember how we had that extra H floating outside? In fact, it's still floating over there, it's still floating over here. When we divide by H, that's going to cancel that. And so when we divide by H and take the limit, X of T plus H minus X of T is going to converge to X minus T. And that's where this is going to come from. Yep. So this is the multivariable chain rule action. And it's telling us no matter what path we take, so long as we stay in the surface, C prime of T is going to be that instantaneous direction of movement. And it's always perpendicular to the gradient of G. So if I'm in a sphere, and I'm traveling like this, and I tell you that's perpendicular to the gradient of G, what's the only direction the gradient of G can come? So I have a pom-pom from the American Math Society. Right? This is my sphere. Okay? And if over here at the top, at the North Pole, I can take any direction parallel to the XY plane, and I'm still going to be tangent to the sphere. And the gradient of G has to be perpendicular to all of those. I can take any direction I want in the XY plane, parallel to the XY plane. What direction does the gradient of G have to be pointing? It's the only direction that's left. Straight up. It's got to be perfect. It's got to be in the normal direction. The gradient of G has to be normal to the surface.
Wait, why is that?
Because what we're saying is, if we take any curve that stays in the surface, C prime of T is your instantaneous tangent. When we had our equation of the line, it's the direction we're moving at that particular moment. And we're saying that that direction that we're moving is perpendicular to the gradient of G.
Oh, because it's equal to.
So the gradient of G is not changing. The gradient of G is fixed. But I can choose my C prime of T. I can keep choosing which direction I want to walk in. And no matter what direction I choose, if I'm forced to stay on the surface, I'm getting that this dot product is always 0. The only way that can happen is if the gradient of G is normal to the surface. If you want, you can think about this where S maybe is equal to 4. And it would be like a slightly larger surface, maybe S equals 5. It's pointing in the direction of increasing. So this has applications for finding out tandem of maximum minimum. As we've just shown, is that if we force ourselves to stay in the tangent, to stay on the surface, then the gradient is pointing in the direction of normal. Well, let's see that with an example. G of x, y, z is x squared plus y squared plus z squared. Let's calculate the gradient of g. That's dg dx, dg dy, dg dz. What's the derivative of g with respect to x? 2x. What's the derivative of g someone else with respect to y? 2y. And somebody else with respect to z. All right, it's screaming pull out a 2, and it's x, y, z. So let's try to think geometrically what is going on. Here is my summative. Here is some point x, y, z on the boundary of the circle. I can write R with a vector to denote the vector going from the origin to my point. The length of that would be the square root of x squared plus y squared plus z squared. So this vector gives me the vector from the origin to the point on the surface. What direction is the normal to the surface? Sorry? What direction is the normal to the surface of this line?
It's just like in the direction then.
Yes, in the same direction as that. The easiest way to think about this is, well, what if we were lucky enough to be going straight up to the North Pole? The normal is going to just continue in that direction. And all you have to do is just like lean back forward depending on where you are. It's the same thing. So for the sphere, it's clear when you look at it, the normal is in the same direction as the radius vector from the origin to the point. And that's exactly what we see over here. That this is just a 2 times vector up. So this is a little bit of a justification. It's not a proof that the gradient to g really is the normal to the surface. And so now, imagine we're at some point, and here's the gradient of g, and this is the same as the normal. Here is some tangent direction to the surface. And imagine the gradient of f is like this. So the gradient of f has some component in the direction that's tangent to the surface. Well, that means if I flow in this direction a little bit, my function gets larger. And if I flow backwards, my function gets smaller. Could I have a maximum in this setting? No. What must be true about the gradient of f if I am going to have a chance for maximum momentum? What direction must the gradient of f be for maximum momentum? So if it has something in a tangent direction, it has some component in any tangent direction, just go in that direction. So I have to have nothing. No matter what tangent direction you give me, the gradient of f can't have anything in that direction. What is the only direction left for f? It's gradient.
For x?
For the gradient of f. What's the only direction left for the gradient of f? It can't have anything in a tangent direction. It has to be normal. We just saw.
Is it g normal?
I'm sorry?
Is it g normal?
So g is the normal of the surface. To be a critical point, so as a candidate for a maximum, we need the gradient of f parallel to the gradient of g. Yeah. So if f is just some function we're trying to maximize, as a candidate for maximum of f. This is going back to what we're trying to do, is try to find optimal values. If we have anything is in a tangent direction, it can't be a maximum or minimum. And so when we get to Lagrange multipliers, this is the theoretical justification for why everything works, for why the gradient of F has to be parallel to the gradient of G. And most of the math is actually going to be algebra and not calculus. That's going to be the hardest part, is solving the equation. But this way, when you actually get to the section in the book and the lectures on Lagrange multipliers and ChainRule, you've now seen a little bit of an introduction. So this was a high level introduction to try to make the sections a little bit more understandable. This is reverse material. Yeah.
So, at a cannon for maximum of F. Okay.
Where F is constrained, where inputs satisfy G of C of T. So these are constrained maximum. You're looking for the maximum value subject to I live on this field. If we didn't have that subject to, well, you just look for where the gradient is up to 0. And then you look for the boundary point. So if you want, maybe I'm trying to maximize a function on and inside a sphere. Inside the sphere, I just look for the gradient f is 0, and then I have to check the entire boundary. And for the constrained maximum and minimum, we just have to use now the gradient of f has to be parallel to the gradient of g. So we will cover this again when we get to the Lagrange multipliers later in the chapter. Yeah. Yeah. This is just, I'm choosing some path C of T that stays on the surface. So no matter what no matter what tangent path I take, at some moment in time, T parallel T, that's going to be my instantaneous direction that I'm using. All right, so I want to end with one last application. Can somebody give me the square root of 121? 11. Positive or negative? All right. Is this a truly challenging problem? No. Why is the square root of 121 not a challenge? Right. And what kind of number is this? It's a perfect square. And I just checked with Mathematica, and it does agree with you. It is 11. What if I want to know the square root of 122? If you had to approximate it quickly, what would you get? A little bit more than 11. So I can look at two different functions. F of x is the square root of x. So f of x is the square root of 121. I actually like the second one a little bit more. Because what am I going to then take back? I will be taking x to be 0, and what other value will I take? 1. Whereas over here, I'm taking x to be 121 and 122. 122 is a big number. 1 is very small relative to 120. What I can do is f of 0 is equal to 11. What's f prime of x? So I have 121 plus x to the 1/2. This is going to be 1/2, 121 plus x to negative 1. Right? Just taking the derivative using the power rule. What's f prime of 0? This is going to be 121 times 121 to negative 1/2. That's 1/22. Now the idea is to use the tangent line to approximate a function. And so f of x approximated f of 0. What? 0. And how much is my last time to get from 0 to x? It's 1 to the power of cube, but it's point x is just x. And so now if we wanted f of 1, there would be approximately f of 0 of f prime of 0 times 1. So the square root of 122 is approximately 11 plus 0.0455. And the square root of 1.2 is 11.0454. Right? That is a pretty good approximation. That's essentially what we've been doing all day. Is taking just a small little bit. This approximation is really good. Here's an example of how good this is. We're moving one whole unit. And look at how close we are, 0.0001. That's how many digits of accuracy we call this. This is an incredible agreement. So we had a lot of ideas. We talked about the three different rules, the three different notations for the definition of the derivative. Each one of them has their own value. We use it to derive what the chain rule should be in one dimension. And then we talked about how we can generalize this to the chain rule in several variables. We talked about implications of that. We talked about level set. What does it mean to be at a level set? Well, it means no matter what path you take, you stay on that function, you stay on that surface. So G of C of T is constant. And then that means C prime has to be perpendicular to the normal to the surface. You're just staying on. So now we have this interpretation that if we have a constraint, the gradient of the constraint is the normal to the surface. And so if we have a constraint optimization problem, then the gradient of it has to be in the same direction as the gradient of G. And the last thing we did was we said, well, how does this actually work in practice when you approximate functions? And so there's going to be a section coming up in the book where we're going to approximate functions, not just of one variable, but of several variables, and just use this again, gradient of f of C of T times C times. That's essentially what we're doing with manual. This is a good place to stop. I will stop the transcript.